for today's MATLAB part, and here let me just click it for viewing. It's all about system responses and signal spectrum. Same drill as earlier, so you know, group of maximum 3 students. You have 1 week to answer the questions. Okay, and fundamentally, the first question is quite similar to today's, or the second exercise. There's small difference. The only differing part is that there's now also 0-point SSS in here. Let's see, can I actually explode it a little bit? Yep, it's barely visible. Anyways, if you make your own copy, I think you can open it up and see what the original picture looks like. It's actually much clearer when you explode it a little bit. So there are those 3 forward term parameters, and then there's of course the same amount of the feedback kind of thing. So when you are doing the difference equation, you do pretty much a similar way you did earlier on the second exercise. So just follow the signal and start writing the difference equation is something. When you have these feedback terms here, you basically move everything of the feedback with the left-hand side y, and remember to change the sign. That's one of the most common mistakes. I should add it on the list. So when you are making a difference equation on generic form, it should look like something like that. Equals to sum of bk x n minus k. And in this, I will give you a little bit more help here, more than you deserve. Okay, the form on this exercise will be something like that. A0 yn a1 yn minus 1 plus a2 yn minus 2. You just have to figure out a0 1 2 equals b0 times x of n plus b1 times x of n minus 1 plus b2 x n minus 2. Okay, these values will form your vector A, which is simply A0, A1, A2. These values here form the system parameter vector B. B0, B1, B2. There. It will be something like that, and you figure out, determine the system parameters, A and B, for that system. And please, this is a good to remember that when you have system parameters for input signals, use B, and then for the output and feedback, use A. If you mix those, the system will become very easily unstable or critically stable if you swap those. Zeros and pole locations matter, so be careful when you are selecting the system parameters, how to call them and how to use them. Then we talk about the impulse response. Okay, we can check the impulse response and then figure out if that, based on that one, is if the system is IIR or FIR. You can guess it already from the impulse response. That actually the after all, the impulse response is of course the official definition of if the system is infinite or finite impulse response system. And you need to justify your answer. Okay, then we go to a little bit closer to the real system. The sampling rate, 8,000 samples per second. And plotting the frequency response for that system. Okay, there are actually commands to do it, so I'll just show them. Okay, then Argon's diagram, zero pole plot. And from that one, you might already start guessing I'll start guessing if where the system, at which frequency the system has highest attenuation. I'm looking for a real physical frequency. Okay, then group delay, which is a derivative of phase response. Then scaling the system. A good filter has unity gain and at bandpass. So there's no gain or attenuation on the bandpass. So we try to keep the signal on our most important the region, unchanged. It's quite simple as that. So basically we will do also scaling of the system. Then some sound sample generation, which is quite similar to the first exercise sound sample. Now there you had the sinusoid. Now you would use chirp signal with certain amplitude, and then in the start frequency at 0 seconds, and then end frequency at 1.2 seconds, and then basically, well, you need to also add some random noise with certain signal to noise ratio. Okay, there at least 60% of you got the signal to noise ratio correct. So if you are uncertain, discuss with your friends here. If you didn't get it right, they probably did. Okay, and yeah, saving it as a WAV file, and then calculating the spectrum, meaning one single spectrum for 1024 points of that signal, just to check where the frequencies are. Then so-called spectrogram, which is a time series of spectra. And then, okay, 10, combining the system responses with the our arbitrary signal, basically. So basically, the question is, can you find the system properties from the spectrogram? Each of you have a different system based on the SS number. So each of you will get a little bit different spectrogram, and there you fundamentally you would probably see how that system changes the spectrum of the signal. Very educational and entertaining. Okay, but I will start with the fundamentals, and let's see, where's the MATLAB? There's my MATLAB. Why didn't I start it earlier? Just for example, I will take one of my favorite systems, And just to get you to use the idea of, okay, we have zeros and poles, and we might actually even design some filters based on zeros and poles. How about if I start with the zero pole plot? So let's see if I actually know the values of zeros. So the zero vector is basically, that's -1. Then I just use for fun semicolon for some reasons. Then we have plus j, semicolon minus j. That'll tell MATLAB, okay, we have zeros and zeros, or roots of the system with -1 j and minus j as the zeros. Then, just for fun, something like that. That looks nice. And that also resembles one of my animations there. Okay. So if these zeros produce on the frequency response, that's Nyquist frequency, that's half of it. That's pi, which is the same as Nyquist frequency. That's half of it. So this system would define those 2 points on the amplitude response. Then we have the poles, so something like that, pk. That looks like 0.4 there, plus 0.4. And then we have an angle pi over 4. So I could actually put here some range. Looks like 0.7. 0.7 times e to j times pi over 4. Okay. And then we also need complex conjugate. Why? We need complex conjugate. I'll tell you in a minute. The other pole on opposite angle. J times pi over 4. So zeros and poles are always as complex conjugate pairs, or they are real. Because when you think of this h of z and the product form, only way you can get real values is that you have say z1 times z minus z1 star. So you must have the in order to get from this multiplication on that product, you need actually real parameters, real value parameters. Only way to get it is to have complex conjugate pairs, meaning basically symmetry over the real axis here. Mirror symmetry. Always complex conjugate pairs. To get real number coefficients of filter parameters. There, okay. So that's one way of defining a system, zeros and poles. New folder, exercise 3, that is. Okay. I start building the system from zeros and poles. You will be starting actually a system building from the difference equation or the flow diagram. It doesn't actually make any change when you start from one point. You will end up having always the transfer function and difference equation. They basically are just different representations, same system parameters. You can start it from different places. Okay, zeros are ZZ equals, what did I say? -1 semicolon plus J minus J. Okay, we're using the semicolon actually to get zeros and poles as a column vector, vertical vector. That's how MATLAB actually makes difference between zeros and poles or system parameters. If you give a vector which has values in one single row, then they are considered as system parameters. If you give a vector which has the column vector, so plenty of rows, just one single column, then MATLAB treats that one as the zeros and poles most of the time. Poles P equals 0.4, point. Remember, point. Decimal point is point. And then 0.7 times exponential of J times pi over 4, right? And 0.7 times exponential of complex conjugate means that you change the J to minus J. Whoops. There. Okay. And let's check how close I did get it to that system. That's done, so I say Z-plane, zeros, poles. Same functions, or the same thing actually works also on the octet, same commands. Okay, now we have the system zeros and poles. How do we get the system parameters? Since this is the basically the product form 0 points. Okay, we can use the inverse operation of roots, which is poly. Polynomial coefficients. Okay, so this will be our BB term, system parameters for forward term, equals polynomial which is defined by those zeros. Right. So that one calculates now the Z to the power of 4 plus something which comes from the cross products, and the last term would be the multiplication of all of those points. Okay, but as I said, MATLAB does a lot of things for you. Wow, isn't that nice and symmetric? Just one, which is actually something that I also expected. Okay, if you have a system of 4 the 4 terms that are equal on forward term, fundamental, that's the same as the 4-point running average system. So 4-point running average has this kind of 0 pole plot. Okay, and then the other system parameters, the A, which is the forward term, that's the polynomial coefficients of a system with the poles like that. Okay. Oh, yeah. Now we had a system. Okay, those are the difference equation parameters, or system parameters for difference equation. They also define the transfer function. On the other hand, transfer function we already defined by the zeros and poles. Okay. So actually then the system difference equation would be I'll just comment this one. So those are the parameters for forward. So we have y of n minus this, that, and that. Let's see if we sorry, didn't want to do that one. Minus y n minus 1 plus that times y n minus 2 times that y n minus 3, and then it has a right hand side term equal to x of n plus x of n minus 1 plus x of n minus 2 plus x of n minus 3. Okay. There we go. That's the difference equation and system parameters. But if you have the, you know, yn is something. I'll just humor you now. The calculation formula kind of difference equation would be here. That has a negative sign. That goes to positive. The next one will have positive sign. That goes to negative. And the last one has a negative side, goes to positive. There. Okay. Be careful with the signs. System parameters. And now we could actually go stem plot the first 10 values of the impulse response. Impulse response, the first 10 values. We first have to generate the impulse function. You know the drill basically. We have the indexes, for example, from -1 to 10. I like to start it with the negative values, and then it shows the difference. So initial state is 0, then it starts hitting the roof. So basically that will give you the 10 first values. or actually 11 first and 1 before. Okay. Indexes. Those are indexes, and then the delta function. Okay, that's a delta function, discrete delta. It's just impulse. And now we can calculate the system response. Filter function is the implementation of LTI system in MATLAB. Okay, the impulse response H equals filter. How does it go? Filter B, A, and X. And if you selected the variable names correctly, you can put those variables there correct way. If you swap the index B and A, then you'll get funny answers. So if you swap these zeros and poles, then you have poles actually on that frequency and that frequency on unit circle, meaning you will get a perfect feedback on those points. So basically the system rings at those frequencies. Okay, so you will get a ringing after the this impulse. So that's a good sign if you basically do a filtering and see why this system is ringing. It's usually because of you mixed the system parameters. Okay, B, A, delta. This is the impulse response. Impulse in, response out. And it looks like this. Wow, that's nice. And from this picture we can already say, okay, this system is infinite impulse response system. We could plot it further, but it's actually not worth of it. Something that I did not yet tell you, but anyways, there is the maximum number, or the highest polynomial number there, which is basically everywhere. You have on that one on the sum, k from 0 to n, k from 0 to n. You also have n zeros and poles, 1 to n, k equals to 1 to n. This highest polynomial that you can see on the transfer function is the same as the order number. Order number of the system. And for infinite impulse response systems, you have non-zero values after the nth element on the impulse response. So impulse response you need to check only up to the nth element, and if that after that nth element you still have non-zeros, then it's infinite impulse response. If that goes flat 0, then you have finite impulse response. Okay, that looks pretty much like a infinite impulse response system, since our order number is 3. third order polynomial, which means 4 values on the system parameters a and b. And here we have, let's see, 4 values there. So after that, 5th value is already non-zero. Okay, that's proof enough. It's infinite impulse response system. Okay. Now just write it here. Infinite impulse response system. Good. What next? Frequency response. Frequency response is easy. Frech. Okay. Let's see if it has the old format. Okay. I'll just show it since there are 2 versions of filter or frequency response on MATLAB. One is defined by the over the object, since MATLAB has been used so much on the filter design, especially that there has been the own package for filter design, which has its own data structures. But we'll just use another form, which is still there, and you can actually browse for help. But that goes so that the format goes that there is a filter parameters b and a. Then there's a number of points where you want to evaluate the system. For example, 1024 points. Okay, this means how many points it will calculate on the frequency response between 0 and sampling rate. And then sampling rate. Fs. I didn't put anything, but I will use, for example, that 2 kilohertz sampling rate. So that's the frequency response if system for system defined by a and b, and okay, there it is. Let's just put it there and then we'll take a closer look. Calculated at 1024 frequencies for 2000 samples per second rate. Okay. And this is basically how you usually would how you usually would show a frequency response. Let me zoom it a little bit, so we'll see some things here. Okay. It has rather flat the passband response. So upper part is the magnitude response or amplitude response. Then it also dips from, so it has some gain, yeah, 22 decibels of gain here. Okay, not a good filter yet, but it drops from 22 to minus 8 dB. Okay, that's 30 decibels of stop and attenuation at the minimum. Okay, so, and then it actually drops down at 500 Hertz right here. Remember, distance goes to 0. So at that point we get 0 magnitude response, which goes to minus infinity on logarithmic scale, on dB scale. And then it also dips down here with this Nyquist frequency. Okay, and I see all of that from that point. Then we get some gain at this frequency, at that frequency, at that frequency. Basically what I did with these 3 points, I kind of eyeballed them in because I've been doing this quite many times. I just eyeballed those so that I will actually, if you take only the 3-point average, then your system response would be something like that. Okay. What I did, I added some poles to add gain on these locations to flatten the bandpass. It also skews that a little bit, so a little bit like that. So closer to unit circle pole, it will add gain at that angle. Okay. All right, I'm quite happy with this system, except on the phase response, non-linear, which is not about being bad filter. It's just that one of the features is that it's non-linear. So it means that it will destroy a pulse shape, but for example, audio processing, that will be just fine most of the time. Okay. But that's the frequency response. Okay, let's take care of first the group delay. And now I need to Google a little bit, since I don't remember if there is a function for group delay in MATLAB. I think there is. There's even a function to calculate the signal-to-noise ratio for a system, but that's, you know, that's for you to find out. One already did find it. Okay, let's see. Group delay in MATLAB. Oh, GRP delay. Okay, I can live with that. GPD is GRP delay of the system. I think it's the same as previous, so BBAA, I would guess this will work. Maybe. Maybe not. That'll be the old-fashioned version. Do we have to change the parameters? Well, I'll just try it. This might not work. I'll just try to use it as the frequency response. No, no, sorry. Ah, it calculates. Ah, okay, of course it calculates since. Yeah. Okay, so it works also the old-fashioned way. I'm a dinosaur, I know. And I'm proud of it. It's nice to be on the top of the food chain, you know. Okay, so yeah, that's the group delay. And the units on the horizontal axis, that's frequency. So that shows the physical frequency. As long as you know the sampling rate of the system, there's absolutely no reason why you would use these angular frequencies anymore. Okay, so if you know the sampling rate of the system or signal, use that one to scale the time correctly, or here the frequency correctly. This one shows the what is the group delay in samples. Okay. Meaning how many samples the signal at, for example, 0 frequency, DC signal. How many samples later it will be appearing with that frequency on output. And here we can see actually the signals at around 250 hertz will appear in average 3.7 samples later than the input. And the most important part is that it gets almost 1.5 samples later than the lower frequencies, which is not good for the pulse shape. But we can live with it. If it depends on the application, we can live with it. It's just a feature, property. Okay, that's the group delay, which is just a derivative of the phase response, meaning phase response is the lower graph there. Derivative of that one. Okay. Next step, how to scale the filter. Brute force approach. I love brute force. Well, I'm Tyrannosaurus Rex. Brute force approach. So, scaling the system for maximum unity gain. So maximum will be unity. First we need to calculate what is the maximum of that amplitude response. Currently we can use this one. This is the brute force. This one calculates the frequency response. It also returns values if you want to. Okay. But we can also use that one, calculate the absolute value. So that is the absolute value, or the amplitude response. In linear scale, and we need the maximum amplitude response. How about this one? Oops. Maximum of amplitude response. Right. Then we just need to save the value. Max amplitude response, MAR, equals the max of absolute value of frequency response. This is not totally correct, would a mathematician say, but, well, you will be engineers. This was close enough. This gives you a pretty close approximation what is the maximum amplitude response of the system. Okay, well, it says max absolute value of frequency response calculated and 1024 points. Numeric calculations. And let's see. So we have basically the gain of the system is 13.32 or 332 in linear scale. So now the question is how we scale the system to have unity gain at maximum. This is the scaling factor for this term. So if we scale, we basically, it's the same as putting one gain block for the flow diagram. So we can basically scale it with something or times MAR, maximum amplitude response value. And it's unity gain, right? Say yes. Okay, so BB, just divide that one with the MAR. In reality, this will change those 1, 1, 1, 1 values to 1 over those. But when you do the implementation, the better way is to just calculate everything and put this gain block at the end. But for analysis, this is the way to do it. Scaling the system for unity gain. And seeing is believing. Let's calculate the frequency response again. Yes, we have unity gain, meaning 0 dB at maximum. All right. Let me go back to the exercise sheet. Group delay, unit gain at passband, then sound samples, and then spectrum. Okay, good. I will be generating a sound sample, but I like shortcuts, so I will just take a already recorded sound sample and start analyzing that one. At the end, also run the signal through this filter. Okay. There's a command called UI get file. Why doesn't get me? Help. Get file name, path name, and just click. Yeah. Okay. That's enough. Opens up a just system browser, and then you can go, for example, the system directory. Let's see, do we have any music here? Sample music? No, we don't have any sample music. You can always find some sounds is on Windows Media, right? And there we should have. Okay, all files. Huh. What? Why doesn't have the media files anymore there? They used to have. Huh. Interesting. Okay, I'll generate something. For sample rate. I start with the sampling rate, for example, that 2000. kilosamples a second. Then, for example, 1 second long sample. Although that would be a funny, I'll try. This one. Okay. A little bit lower so we can actually see something. So that's one of the standard sampling rate. Just to be on the same page with the, the sound card here. And then sample time vector from 0, for example, with this time step 1 over fs until the time is reached, say, 0.8 seconds. That will be time vector, sample time vector 0 to 0.8 seconds with sampling rate fs. Okay. I just thought something on the sinusoid. Okay, this is our signal. Xx equals 0.3 with its amplitude times sine times tau times pi times, I'll use 440 Hertz just for fun, signal frequency times t. Okay. I'll just also add some noise here. Random numbers, size of sampling time vector times 0.2, which would be the standard deviation of that noise. So what is the signal to noise ratio here? Calculating the signal to noise ratio would be 20 times log 10 of the signal variance. If we signal standard deviation, which is 0.3 divided by square root of 2. If it had a amplitude of 1 sinusoid, then this standard deviation is 1 over square root of 2. It's same as root mean square value. And then we have the 0.2 there, so we have 0.5115 signal to noise ratio. Okay, so it's not really good signal. We just have barely more power on the signal than in noise. However, let's calculate something here. For example, one single spectrum. Subsample. With XXS or XX1. I take first just certain section of those samples, and I will use usually 2 to the power of something numbers, because, well, discrete Fourier transformation. If you do it in fast Fourier transformation, so you basically have to take power of 2. Okay. XX. From the beginning, 1 to, say, 2 to the power of 12 samples. Yeah, that's good. So we have 4,000 something. Maybe. Well, let's take one. So 1,024 samples from beginning. Okay, use power of 2 samples to get benefits of fast Fourier transformation. Okay. Then we calculate power, which means that we take. Oh, okay. Where did we have it. All right, let's take a quick look. Okay, we need to calculate the Fourier transform of xt times complex conjugate of Fourier transform of xt. Oh, wow, that's nice. There's already the formula here for MATLAB. So power is 1 over n times fs times ffTx, complex conjugate of f. So basically that beginning of it, it's just a constant. You spread the power on the right amount of blocks. Okay. So power spectrum. Would you close the door? Okay. Okay. So power spectrum, pxx equals fft of xx1 multiplied element by element, complex conjugate of fft xx1. Okay. Okay, now we get rid of that distraction. Yeah, it was distracting me. Right, so then we need the scaling factor, but usually I don't scale these signal things. Anyways, if it will be in decibel scale. Okay, so it's always the relative to something. Of course, if you want to scale it directly to some values and have a reference value there, then you should do some sort of calibration of the system in any case. Good luck with the calibration with these sound cards of the computer. Okay, this is the unscaled power spectrum. Okay, done. What now? We need to do the mapping. I talked something about the mapping, that if we have the discrete Fourier transformation maps these samples so that it actually samples those or maps the frequencies from 0 to sampling rate. Okay. Frequency mapping. We have 1024 points also in discrete Fourier transformation, and the first frequency is 0, the last one is almost the sampling rate. Not quite. Okay, but the frequencies there, FF, they have 1 to 2 to the power of 10. Okay, that takes care of having this sampling on the frequency scale. Same the way as mapping on the time scale. You have indexes from 1 to 2 to the power of 10. However, our first value will be DC, which is 0 frequency. We then subtract 1 here. We still have that 10 to the power of 10 frequency samples here. And then this one is mapped so that basically you have the sampling rate. So, or let's do it this way. You multiply that with the frequency frequency resolution. Now I'm mumbling, sorry about that. So you scale it by the frequency resolution. So this is the same way as we mapped basically this indexes time TS, sampling time, which is the sampling time is same as the time resolution. Now they have the frequency resolution, which is the sampling rate divided by the number of points on this discrete Fourier transformation. Okay, that's the mapping. Next, we can plot it, but not quite yet. That's power. I told something about the decibels. Okay, when we have a power spectrum, or usually power anything, then the units is decibels. So dBPXX equals 10 times log of 10 of pxx. It's already power, so we just need to make 10 log 10. And it's now you can see it's unreferenced decibels. Well, we lost the scaling already, so it doesn't make any difference here. We could actually scale it so that the least significant bit, or the, well, full tilt of the A2D converter is 0 dB. But this is as good. And then we can plot. X is FF, then we have dBPXX. Wow. Okay. What is wrong with the picture? Nothing. Absolutely nothing. Just a reminder that, you know, it's the in spectrum space everything is symmetric. The systems on spectrum space is complex spectrum. So we have symmetry over the real axis. Same thing here. Since if this was pi, it's also minus pi. And in frequencies, it's Nyquist frequency or minus Nyquist frequency. And when this Fourier transformation starts, it goes that way, all the way to 2 pi, or sampling rate. Okay, which means that somewhere in here at the middle, let me add some line here. X values would be sampling rate over 2 and sampling rate over 2. That's the Nyquist frequency. Y values would be minus 20 and 50. There is the Nyquist frequency, that blue line. We don't need to show more than to the Nyquist frequency. Same way as for the systems, the frequency response is showed only from 0 to Nyquist frequency. Here we don't need to worry about that right hand side part at all, since it's just mirror symmetry. Okay. So fundamentally, we could just plot, let me remove that one, plot the first half. There. Perfect. Power in dB and the frequency in hertz. It just needs some labels. And we can clearly see that even though our signal to noise ratio was just 0.5, since we have concentrated the signal power on signal frequency, we can, it's basically on this scale, it's, let's see, 10 dB, about 30 decibels higher than the noise floor, easily recognizable. If we go on smaller delta F, we even get better resolution and better concentration of that peak. This is how it's just calculated. Okay. Easily located. Okay, that's a single spectrum. Then we still have the spectrogram and filtering of the signal. Okay? Spectrogram. If you are using Octave, you might actually need to check closer what kind of spectrogram functions there are, since they are always changing. Okay, but I can actually take a look at those. However, the MATLAB spectrogram function is excellent, except it plots everything in a funny way. I'll show you the correct way. So, easy to use. You just put the, actually that's the way I usually call it, spectrogram of signal with the window size, or actually you can also put their shape, number of overlapping bins, and how many points you take into transformation, and then you can also add there the sampling rate, and then you can add there one more parameter. How this okay, that's basically what the spectrogram might actually look like after some work, but let's see how do they, yeah. So this is the mathematician's point of view, how the spectrogram should look like. Do you see anything funny on that picture? Overall, if you have something changing by time, where would you put the time axis? I would use a x-axis for time. Right. If you put time axis as y-axis, would you put it so that it actually grows from here to there? I wouldn't. I wouldn't. Even, you know, all the text what we produce, we will take, you know, time goes that way, or from left to right. Well, most of the cultures, but not like that. Fortunately, they are also providing one parameter that you can define which axis is which. So in this picture, there's absolutely nothing wrong with it. Okay. So, how to calculate the spectrogram of the previous signal? And the spectrogram, yes, that's just an image showing how the power or spectrum of the signal changes by the time. Hot colors or high values there means that there's a lot of power. Cooler colors, less power. And here I use the whole the full data. That's 0.8 seconds what I had. Window, that's basically window size or window shape. We'll talk about windowing later on next week, actually. But here, this is just basically a value how many samples you would have, or what size of the data you will take into account for calculating the spectrogram or spectrum. Okay. So something divided by 2. Number of overlapping bins, meaning, well, you have the data. Does it fit here? Oh, yes, it does. I'll just use that one. You have the full data here, the X. Then you have the window size, which is basically the window, which is basically the region of interest. Okay? Window. Next one starts somewhere. So how many overlapping bins you want to have on your next window. So that's the number of overlap. Then I would use, say, half of those. So 128. How many points you want on the Fourier transformation? Well, this defines your spectral resolution. And you can actually have the same as window or wider. Increasing the basically the width, then it basically just calculates, adds some zeros and calculates the spectrum. Yes, the spectral resolution gets better, but you don't gain any new information. Okay, but you can add more points to calculate better resolution for that small window. So basically this would be just zeros. NFFT. Okay. I use always the same as window size. I haven't found any use for that other number yet. Sampling rate, if you know it, yes. It'll be nice to put there too. Then there was that parameter y-axis. Was the last parameter on the help file. Unfortunately, the online help or the immediate help doesn't help. Click enter, yes. That's our spectrogram. My signal didn't change. The frequency was, well, just single frequency sinusoid signal, so from 0 to 800 milliseconds. That yellow line shows a frequency at 440 hertz, roughly 440 hertz, which frequency is the closest to the unit spectral resolution. The changing part there, the speckle, that's the noise. That's the noise floor. Okay. So now we can calculate spectrum of the signal and spectrogram. Chirp, I would expect a straight line. Okay, on the exercise, you start on some frequency from the 0 seconds, then it increases the frequency, so it's actually upslope on that spectrogram. Okay, so yeah. Let's take a quick look what happens for the signal on the system. We have the system which was defined by A and B, and this signal XX. So I can calculate the system output will be same way as we did the impulse response or same way you can also do the step response. You just feed in step. Just putting here the signal. Okay, that's the system output for exec input. This is audio sample. It's no use to show it on plotting it. It's a long sample, but yeah, we can run the spectrogram. Okay, so spectrogram. This is the original signal. There. I take another figure and put YY there. So this is the filtered signal. And oh yes, the system did something for the signal. And there you can see actually it's quite informative picture. All right, that's how to put this one. Does it go there? Yep, it does. Let's put them side by side. We still have the same 440 Hertz signal there. Okay, then it seems that something happened on the top half. Yes, this is, as you remember, this is the low-pass filter. It has a 30 dB attenuation on the higher frequencies. That's the blue part there. So those higher frequencies here are because of the attenuation. Then there's that blue stripe. You can roughly see it because of or actually one blue stripe here and another there, which means low signal strength. Okay, and they are basically those notches or those places where the filter response goes to 0 only at the exact frequency. Okay, but these bins here are quite wide. We use 256 points, which means that each of those bins there, let's calculate quickly. Spectral resolution. So we used sampling rate, Fs divided 256. So this is same as sampling rate divided by the number in FFT. So we have 43 Hertz resolution. That then everything starts to make perfect sense. We also have on those bins which has the notch or the 0 the response on those frequencies. But that when you do the frequency response, that bin there, that frequency bin also consists of the noise around 43, within the 43 Hertz range on the notches. Okay, so you get speckle also there. All right, I will take a quick look at the I have been using my voice enough now, so now you can start working on the third exercise. If you still, okay, I see a lot of you are already still working on exercise 2. 2 days was the exercise deadline, but I will give you a hint. I won't be checking those until tomorrow morning. Okay? I have absolutely no time for today go through the exercises, so I will, you know, if I cannot keep my deadlines, I'm not expecting you to keep the deadline. So you fundamentally you have time for tomorrow morning around 7 a.m. to actually return them without any penalty. Okay, thank you. Show is over, you can stop the recording. I will stay here until, well, cows go home.